Alright, let's move on to relative motion part 3. Relative motion part 3. So we've been dealing here so far with a guy, and let's just go ahead and put him in an elevator. And there he is. And he's got a ball that he has kicked up from the floor of the elevator, and it's moving up with some initial velocity v naught. V naught is initial velocity of ball with respect to elevator. Okay, so the elevator, we're going to do it by the letter E, and then we're going to denote the ground with the letter G. And each of these, the elevator has a y-axis associated with it, starting from the floor and going up, and the ground has a y-axis associated with it, starting from the ground and going up. And so we can say anytime y for the ball in the grounds frame is equal to y for the ball in the elevator frame plus y of the elevator in the ground frame. That's just saying that at any given time the height of the ball above the ground is the height of the ball above the elevator floor plus the height of the elevator floor above the ground. And we developed this whole subscript thing where you can take BG, BE, EG. And then we showed in the last one that, let's change colors just for fun, that velocity of the ball with respect to the ground is velocity of the ball with respect to the elevator plus velocity of the elevator with respect to the ground. And so we also showed, that for, if the elevator is moving up at some constant velocity, then the apparent velocity of the ball with respect to the ground will be, shifted upward compared to the velocity of the ball with respect to the elevator. So that's great. There's also, just to sort of put a human face on these things, there's also a person standing outside on the ground who has, x-ray vision or whatever, and he can see through into the elevator. So he sees the ball moving around, and the person in the elevator sees the ball moving around. They see it slightly differently because they're in different places. So finally, we want to talk about acceleration. So what we did to get from position to velocity was we just took delta for position and then divided by delta t to get to velocity. So as you might imagine, we're doing basically the same thing to get to velocity. So this equation is true for all time. As long as there's a ball, an elevator, and a ground, and they're moving within that one dimension, this will work. So you can say if that's true, then if there's a change in the left side of the equation, then the right side of the equation must change too by the same amount. Not hard to imagine. Okay, the next step is to look at this part and say, well, if the sum of the ball elevator velocity, the ball's velocity relative to the elevator and the elevator's velocity relative to the ground changes, then it must mean that one of these two changes, or they both change, and somehow the sum of their changes is the same as the change in their sum. So I'm just going to bring that over here, and what it really means from a practical point of view is we can distribute the delta. So delta V BE plus delta V EG. Okay, and then we divide everything by delta t. Delta t, delta t. Well, what's the definition of velocity? What's the definition of acceleration? Change in velocity divided by change in time. So what this gives us then is that the acceleration of the ball with respect to the ground is equal to the acceleration of the ball with respect to the elevator plus the acceleration of the elevator with respect to the ground. Now, this, seems kind of pedestrian. It seems like, it probably seems to some of you like sort of a logical outgrowth of this. And in fact, if you're doing calculus, you can just say, oh, well, yes, if this is true, then we just take the derivative of both sides, and that's got to be true, and that's what we get. So it works from that perspective as well. I'm just deriving it the non-calculus way. What this means, depends on, what it means is that acceleration, we can get the acceleration in one reference frame from the acceleration in another reference frame and the rate at which the two frames are accelerating with respect to each other. So let's take, for example, and I'm going to page this down a bit. That's good. All right. Let's take, for example, I'm going to call this example 1. Let's take a case where the elevator is accelerating upwards. So there's our elevator E, and there's a dude inside with his ball. The ball is B. You can barely read that. And then here's the ground. G. So, ball right there. All right, so let's say this guy, the elevator is accelerating upwards. Elevator accelerating upwards, rating up at, say, 5 meters per second squared. All right, and we're going to say here g equals 10 meters per second squared. I'm going to use that instead of 9.8 just because it's a little more convenient, and there's no, you know, you can do all the physics with 10 that you can do with 9.8. You'll be 2% off, but you know, it's a lot easier to deal with 10 in math than 9.8 and do the stuff in your head. And I don't want to pull out the calculator here. I want to focus on the physics. So what's happening here, let me switch to green. What's happening here, this is, so this, what's our variable for this using this scheme? It's the acceleration of the elevator with respect to the ground. So acceleration of the elevator with respect to the ground equals 5 meters per second squared. And you can say plus 5 meters per second squared since it's going up. The ball is accelerating with respect to the ground at negative g. Acceleration of the ball with respect to the ground is negative g. There's negative 10 meters per second squared. So let's say we want to find what's the acceleration of the ball with respect to the elevator. Right? So, well, we take this equation here. Just take that and plug these things in. Remember, and you know what, even if we didn't have this equation handy, we could still put one together using our subscripts. So we've got acceleration of ball with respect to ground, acceleration of ball with respect to elevator, acceleration of elevator with respect to ground. Now we know, you know, let's say we remember that we can add up two of these things and get the third one. Which ones do we add up? Well, which ones can we sandwich together and have you know, the subscript at the beginning of the second term match the subscript at the end of the first term? And that is pretty obviously here and here. So we can take ABE plus AEG equals, and then so we, you know, sort of smash these together, let the E's annihilate each other. You know, it's sort of what we're doing, like the E's are sort of canceling out. Okay, is ABG. Well, there we go. So take this over. Acceleration of the ball with respect to elevator is what we're trying to find, right? ABE plus acceleration of elevator with respect to ground we have right here, plus 5 meters per second squared, equals acceleration of the ball with respect to the ground, negative 10 meters per second squared. And what that gets us then is right here, the acceleration of the ball with respect to the elevator is going to equal negative 15 meters per second squared. So what this means really is that this guy in the elevator, from his point of view, when he, you know, when he kicks the ball up in the air, it's appearing to sort of, you know, get pulled back down to the floor faster than it would be if the elevator was standing still, because the elevator is accelerating upwards. Acceleration of elevator with respect to the ground is upwards at 5 meters per second squared. So, and this is an important result. It means basically that if you're accelerating, if you're in a box that's accelerating upwards, or if you are in a frame of reference, if you're standing on something that accelerates upwards, to you, gravity appears to be greater. We can remember that if you're in, say, a tall building, you know, and you get in, say you get an elevator on the ground floor, and it starts to go upward, you probably remember that at the bottom, when the elevator is accelerating, you feel greater gravity, right? You feel sort of pushed down. You feel like your stomach is sinking a little. You feel, you know, like you're being, like this invisible hand is sort of grabbing you and pushing you down a little towards the floor. And then at the bottom, I'm sorry, at the top, the elevator is decelerating. So, well, it's accelerating downwards. So it's slowing down as it comes up to the top and coming in there for a landing. And as it slows down when it's going up, it's got an acceleration downwards, which is a negative acceleration. And so in that case, you know, for example, if, I'll do this in different colors to keep it separate, but if acceleration of the elevator with respect to ground then is negative 5 meters per second squared, and you plug that in here instead, then what you'll get is the acceleration of the ball with respect to the elevator is only negative 5 meters per second squared. And that means the ball is going to take, if you kick it up, the ball is going to go higher and take more time to come back down to the ground as though you're under lower gravity. So I think you can remember that you feel heavier when the elevator is accelerating upwards and lighter when it's accelerating downwards. And then when you come back down, the elevator starts accelerating downwards, so you feel lighter at the beginning of the trip, and then you feel the same, normal weight for most of it, and then at the end, you feel heavier as the elevator is accelerating upwards to bring itself back to a stop. I'm going to talk a little bit more about this in one more video.